Hello everyone, last time we talked about 71% of the total energy budget of the universe is occupied by dark energy. But how do we know that dark energy exists in this universe? That's the subject of today. So let's get started with the Hubble's Law. We previously discussed about this Hubble's Law. This is plotting the recession velocity. Each galaxy is moving away from us against the distance. And as you can see, the more distant galaxies are moving away from us faster. And this is the evidence of the expansion of the universe that Hubble discovered in 1929. Because if you imagine a universe like this bread with raisins inside, if the bread is expanding, then the distances between each raisin are getting larger and larger and larger. The distances between more distant raisins are getting larger faster. As you can see, this raisin is moving away by 5 centimeter to 10 centimeter. But this more distant raisin is moving from 10 centimeter to 20 centimeter. So at a faster speed. Exactly like this Hubble's plot. More distant galaxies are moving away from us faster because just like the raisin universe, our universe is like that too, expanding like that too. Okay, so this was the discovery of the expansion of the universe. More recently, two teams of astronomers used type 1a supernovae to map out the expansion of the universe. So this is a supernova explosion here, bright star. This is an explosion of one star, but it's much brighter than its host galaxy. This galaxy has 100 billion stars inside. But this one stellar explosion, one supernova explosion, is as bright as remaining 100 billion stars. In fact, this supernova explosion is 1 million times brighter than C5 variable stars, which Hubble used to map the expansion of the universe. 1 million times brighter means we can map out the expansion of the universe much more distant universe. So we can do that. Reason why supernova explosion is bright is this is a schematic animation of the type 1a supernova explosion. Astronomers believe type 1 supernova is one white dwarf star and one companion star. Let me start the video again. As the companion star ages, it emits some material like dust and gas. And this material is accreted on white dwarf star, and then white dwarf star getting more and more material, and when it reaches 1.4 solar mass, 1.4 times more massive than the sun, it reaches the so-called Chandrasekhar limit. This is the limit. Degenerate pressure of the electron cannot sustain the large gravity anymore. Then these white stars collapse and explode as a supernova. Let's see the video. Accretes, and it reaches Chandrasekhar mass, which is 1.4 solar mass, and then type 1 supernova explodes. Because type 1 supernova always explodes at 1.4 times solar mass, so the brightness of the type 1 supernova is always the same. Then if the brightness is always the same, we can use type 1 supernova to measure distances. Because if we know the intrinsic brightness, if the supernova looks faint, that means the supernova is farther away in the universe. If the supernova looks bright, then that means supernova is in the nearby universe. It looks like a candle. We know the brightness, and you put it far away, then it's faint. If the candle is closer, then it's bright. So we call type 1 supernova as one of the standard candles. Okay, Then those two teams of researchers use this type 1 supernova to map out the expansion speed of the universe. And this is their Hubble diagram. Again, the redshift, and in this case, they are plotting magnitude, how bright those type 1 supernovae are. And then fainter, the magnitude a larger number. Each points here are supernovae. Okay. Then, very surprisingly, if you look at these data points, and these supernova's brightness were a little bit fainter than expected. Expect this line, but those supernova data points are above this line. Above means fainter. That is because the expansion of the universe is not just expansion, but expansion speed is accelerating. That's why those supernovae are a little bit fainter. So this is the discovery of the accelerating expansion of the universe, and this acceleration is because of the so-called dark energy. There's a mysterious energy called dark energy, and this dark energy is accelerating expansion of the universe. Because of the discovery of this dark energy, those three gentlemen received the Nobel Prize in 2011. So that's how we know that 71% of the energy budget of the universe is the dark energy. So that's a big discovery, but however, it remained as a question. Then, what is this dark energy? Dark energy is everywhere in the space. It's associated with space. So even here in this space, there's a little bit of dark energy, or even in front of you, anywhere in the world, there's dark energy. If there's space, there's dark energy. And then dark energy is a little bit pushing the expansion of the universe. As a result, expansion of the universe is accelerating. Then what is this dark energy? I said it's associated with the space, so you might think about the zero-point energy in quantum mechanics. That is also associated with the space. So in quantum mechanics, there's something called Heisenberg's uncertainty principle, and then position and the momentum cannot be decided so precisely. There's always some ambiguity in quantum mechanics in a very small Planck scale level. So even if you cool down the temperature to absolute 0 degree, the position of particles are still uncertain because of uncertainty principle. So if it's uncertain, there's energy there. So this energy is called zero-point energy, may be the source of the dark energy. Let's compare the energy scale. So dark energy's energy scale is about 10 to the minus 24 gram per cubic meter. Okay, and this quantum zero-point energy, sometimes called vacuum energy, is 10 to the 99 gram per cubic meter. As you compare these two numbers are very different. In fact, orders of 122 difference between these numbers. In a way that vacuum energy is order of 122 too large to be a dark energy. A lot of people confuse it here, but actually dark energy is much smaller than the vacuum energy or zero-point energy. This is the biggest discrepancy in physics theory and observation. If something is different in order of 122, these two are probably not the same thing. Order of 122 is much bigger difference between elephants and ants. So these two are two different things. So the dark energy still remains one of the biggest mysteries in the physics. If you can solve this puzzle, I'm sure you will get the Nobel Prize. Okay, was it interesting? If you have any question, please ask below. If you like the video, please subscribe. Okay then,